and we'll do friction after this. So the model that I'm going to show you is based on something called a law, and it's due to this person named Hooke, H-O-O-K-E, and the apostrophe S is the ownership. So this is Hooke's law. And I'm going to describe to you a Hooke's law inspired model. And here's the idea. Here is a spring, and it's connected to a massive object. And I'm going to say that there is a special situation for the spring such that the force on M by this spring is equal to 0. So this is true when the mass is, say, located right here. This position is often referred to as the equilibrium position, or equilibrium extension, or something like that. But if I stretch the spring, so let me pull the spring out, you know, like an everyday normal spring or rubber band, if you stretch it out, it pulls back. And so if I cause this little mass to move over from equilibrium, then I have extended the spring out of equilibrium. And I'll say that delta x is this vector displacement of the mass over this way. This displacement is a vector, right? It points from the equilibrium position out to the location of the mass. And the idea of Hooke's law says that the force on M by this spring is equal to, it's proportional to a Hooke's law spring constant. So for the spring, some constant, multiplied by that displacement vector. But remember, if the displacement is over to the right, we expect a spring to pull backwards. And so we put in this extra minus sign. So this spring constant has a lot to do with the material of the spring. This spring constant is independent of the mass that you stick on the end of it. And it's also independent of sort of how you treat it, at least according to Hooke's law, and our basic model. But this spring constant is going to have units, right? It's going to give us a force if we multiply it by a distance. So this is going to have units of something like newtons per meter in the SI unit system. Of course, if the spring has been scrunched, so here is the location of the mass, this is equilibrium, you can see that this delta x vector actually points the opposite way. So that's the displacement of the mass from equilibrium, or it's actually the displacement of the end of the spring from its equilibrium length. And you can see that even following the very same formula, it's pushing out. So if the displacement's left, the force is right, for example. Yeah, and so this is a Hooke's law inspired model for a spring. Rubber bands are kind of like weird because you can have a rubber band, and if you just pull it out straight, it still won't pull back on your object, but it'll start to pull back on your object if you extend it out further. So there is a force backwards. But if you take this mass and you put it over here somewhere, then the rubber band goes slack and there is no force. So rubber bands don't get modeled like a spring. But you could kind of model, well, you could model the rubber band to pull back if the length of the rubber band is, you know, beyond its equilibrium length, and then otherwise the rubber band doesn't put a force on the object at all. It does not ever push out on your object. So that's a spring tension model. So as promised,